Okay, today we're gonna prove two propositions which are very important. The first proposition is called the monotonicity of measure. So monotonicity of measure. We already have seen that we do have a monotonicity in terms of Lebesgue measure as well, and also we do have monotonicity for measures. So the proposition statement says that, so this is a standard setting. Suppose x as mu is a measure space, and we have two sets. Suppose DE belong to S such that D is contained in E. Then so measure of D is lesser or equal to measure of E. So first and second is part of corollary, which says that measure of E difference D is nothing but this is measure of E minus measure of D, but condition is that measure of D should be finite. So to prove this, I think we are gonna use some set theory. So Venn diagram, like suppose if this is my E set, okay, and then I do have D. So suppose this is my D, okay. Now what can I say about this area? So this whole region is nothing but this is E difference D, and now you can see that E difference D and D, they are disjoint set, and the union of both is nothing but E, right? So we can see that E is nothing but this is E difference D and union D, right? And they are disjoint. Now if they are disjoint, we can just go ahead and use the second property of measure, which says that measure of E is nothing but this is measure of, since E is E difference D union D, so then they are disjoint. So by the second property, this is measure of D plus measure of D, and this is nothing but this is greater than measure of D. Hence we are done that measure of D is less than or equal to measure of E whenever D is a subset of E. So, and also we can see that if we just forget about the inequality that we just had, so we can see the from the equality we can also clearly see that measure of E difference D is nothing but this is measure of E minus measure of D, but we assume that measure of D should be finite. Why measure of D is like, why it is finite? So suppose if so we can clearly see that if measure of D is suppose infinity, then clearly measure of E is also infinity. Then we will have, so measure of E minus measure of D, D is infinity minus infinity, and we don't want this, so which we don't want, okay, which we do not want. So that's why we put a condition that okay, measure of D should be finite. And now we are gonna prove a second result, which is the union of measures, okay, or measure of a union. So now we have a measure of a union. Again we are gonna use set theory. So again the same setting, we have XS is a measure space, and now we have DE belong to S, and with now measure of D intersection E is finite, okay. Then so measure of D union E is actually measure of D plus measure of E minus measure of D intersection E. So again we are gonna use set theory, Venn diagram. So now suppose if we have, this is my D set, okay, and suppose this is my another set which is called E set. Okay, so then this area is nothing but this is D intersection E, and this area we can say definitely it is D difference D intersection E. And also this area is nothing, this whole area, this is D, now E difference D intersection E. And now we can see that all these three sets are disjoint, and if we take the union of all these three sets, we're gonna get E union D. Okay, so then D union E is nothing but this is D difference D intersection E. Okay, union D intersection E, and union E difference D intersection E, and they are disjoint. If they are disjoint, we can just go ahead and use the property of the measure, second property of measure. So then measure of D union E is nothing, but we can directly, as we know that what is measure of D difference D intersection E, this is nothing but this is measure of D, okay, minus measure of D intersection E, and plus measure of D intersection E, and then plus measure of E minus measure of D intersection E. So this is nothing but this is measure of T minus plus measure of E and minus measure of D intersection E. Hence we are done. But just, you know, it was very easy, just we need to use the set theory. Okay, so we are done for today, and thank you, hope you understand.